True or false if a 4 by 4 matrix with a row of 0 is non-invertible? Has to be true, because for part A, if you take any matrix with rows 0, 0, 0, 0, and you could put whatever you want here, A1, A2, A3, A4, B1, B2, B3, B4, C1, C2, C3, C4, this is definitely, this matrix has a 0 determinant, because if I go across the first row to find the determinant, every element is 0, and if I'm multiplying the cofactors and co-minors by 0 on each step, the determinant of this matrix will equal 0. And if the determinant is 0, that means it cannot be inverted. So you have to provide an example like this. Cannot be invertible, meaning there's no inverse. Okay, part B. Every matrix with ones down the diagonal is invertible. No, not necessarily. False. Because whether you have ones on the diagonals or not, that's not what determines whether the matrix has an inverse. What determines whether the matrix has an inverse is if the determinant does not equal 0. That's what determines if it has. For example, if you were to take matrix 1, 1, right? This has ones along the diagonals. Okay, well, what if I put 1, 1 here? Or minus 1, minus 1? Then what's the determinant of this matrix? Then the determinant of this matrix will be 0, even though I have ones on the diagonal. So it still has no inverse, even with ones on the diagonals. So definitely this is a false statement. And part C, it says if A is invertible, then A inverse and A squared are invertible. Well, A inverse is definitely invertible, because because A inverse will get me back an A, right? So if a matrix A is invertible to give you A inverse, then definitely A inverse has to be invertible so it can get you back A, right? So that's a true statement. Now now let's take a look if A squared is, so this is true. The first one is true. The first part of the statement that A inverse is invertible is true. The second part is A squared invertible. So why don't we take, if we were to take A squared and inverse it, this is the same thing as A to the minus 2, which is the same thing. I could rewrite this as A inverse squared, right? And since A inverse exists, then A inverse square exists, because if A is invertible, A inverse exists, which means A inverse square exists. Therefore, yes, A squared is invertible. So both components of this statement, part C, are true.
That means that the determinant's not going to be 0 if the determinant